Hi, thanks for tuning in for the pre-lab exercise and demonstration for melting points of organic compounds, part of the Gen Chem 2 laboratory curriculum at York College, Pennsylvania. In today's video, we'll be examining how we can use melting points to accomplish the two primary tasks that they are used for in organic chemistry and chemistry in general. And because the materials are pretty small, I'm going to attempt to be zoomed in as a little bit differently than when I'm in front of the board for today's pre-lab video. So we've got two purposes for melting points of organic compounds. One is for the identification of compounds, which is always done by comparison. We can't just take a material's melting point and then use that as a means of identifying or verifying something's identity, because many compounds would have similar melting points. So we would always have to do a comparison to a pure sample of the compound that we think is perhaps a compound in question. And that technique, when we do that, we'll learn about it today, is what's called a mixed melting point. The other method that melting points are used is to determine the purity of a sample. Only a very pure sample of a compound will have a narrow melting point range, which would be less than 2 degrees Celsius. A wide melting point range, something greater than 5 degrees Celsius, would be an indication of an impure sample. Okay. And as I walk you through the experiment a little bit, I think you'll come to understand how we'll use this information in today's lab to try to identify an unknown compound. So, as I zoom back out a little bit, we can see the melting point analyzer, as it's called, the piece of equipment that we'll be using today. Now, in conjunction with the melting point analyzer, we use very thin or small capillary tubes. As you can see, I'm holding one of these up, and it's only about as big as a finger. These tubes have a small amount of the material of interest placed into them, and then they are inserted into the melting point analyzer, into small slots that are in the analyzer. And there is an eyepiece through which you watch the sample as you heat it. So you would activate the heat, which is really nothing more than a light bulb, a fairly intense light bulb, whose brightness and therefore the amount of heat that it's producing are controlled by a very small dial here. Okay? And then this is attached nowadays to a digital thermometer. An old-fashioned one would have had a traditional thermometer inserted into it here, but now we have a digital thermometer that would be connected to it. And as you add heat, the temperature goes up, and you're watching for the sample to melt. Now, when a sample melts, it actually melts in a range, not at one exact temperature. And so when we use the term melting point, it is most properly used as a melting point range. And that's why I was referring to having a narrow or a wide range as your experimental melting point. You'll be looking for, when you see the zoomed in version of your sample, you'll see the little tiny crystals as solids. And then as the sample melts, it will first start to appear to sweat, but you'll certainly see some melting when a little bit of liquid shows up at the bottom, and yet a few crystals are remaining. This would be the start of your melting point range. You would record the temperature at that condition, and then when the last of your crystals has melted and all of the sample is now liquefied, that would be the end of your melting point range. And so if this first value occurred at, let's say, 78.2, and this value occurred at 79.4 degrees Celsius, the melting point range would be 78.2 to 79.4. You don't average them, you report that range. This range is 1.2 degrees Celsius wide. That would put it into the narrow category. And so this sample that we would have potentially been observing is a pure sample, we can conclude. As opposed to if this had started at 78 and ended at maybe 85, that would have been a 7-degree wide sample. There would be some impurity or in that sample. Now, impurity actually means a mixture of things is present. Okay? And we can prove this concept to ourselves by studying the mixed melting point. Two samples that have identical melting points, if we mix them together, will have a different melting point range. So if I had, and I'll use different colors, a black material here in black marker that had our 78.2 to 79.4 range, and then I had another material that was the red marker represents, that was also 78, let's say 0.4 to 79.8. These materials have essentially the same melting points. When I mix them, though, one of the interesting things about mixtures, all mixtures have melting points that are lower and wider than their pure counterparts. So this mixture, even though it is made of two materials that melt at the same values, would potentially have a melting point, probably, it would vary with composition, but maybe 70 to 75 degrees Celsius. So you can see that it's melting at a temperature lower than either of our pure compounds and in a much wider range. Okay? Even though you would have seen these pure melting points here. And that's how we can use melting points for both identification and purity. If you think your material, if you had the black sample here, and you think you know what it is, you would measure its melting point. You would also measure the melting point of the known material that you believe your material is. Okay? Then you would mix the two. Okay? If the two are different materials, their melting point would be wider and lower. If the two are in fact the same chemical, then they really aren't red and black. Then they really would both be the same compound, and we would expect the same melting point range that we had in the individual experiments. And so today, the first part of your exercise will be to confirm this concept. You will melt two compounds that do have very similar melting points to one another, urea and trans-cinnamic acid. So you'll confirm that they are like these two materials, have similar melting points. Then you'll mix them and see for yourself that you get a wider, lower melting point. Then you'll turn your attention to an unknown compound. And you'll measure your unknown compound first. Then from a list that you'll be provided with, you will guess, or not guess, but you will try to determine which compound on the list, this is on page 22 of your lab manual, your compound is. So when you determine its melting point, as an example, let's say I had an experimental compound whose melting point today came out at about 157 to 159. According to the table on page 22, This is pretty close to salicylic acid. So what I would do is I would generate a sample that is a mixture of my unknown plus my known salicylic acid. Okay? So if my unknown was in red and my black's salicylic acid. If this mixture continues to melt at 157 to 159, that is confirmation that the unknown equals salicylic acid. If this mixture melts at any other temperature range that is lower than 157 to 159 and wider, then it is not, the unknown is not salicylic acid, because it would be a mixture that we have over here that I was referring to earlier. Okay. All right, all that's left to do, I think, is to demonstrate how we get our samples into the melting point analyzer. And it's just a little trick that takes some practice. So I've prepared a compound here. Usually we put it onto a watch glass, okay? And that just spreads out our compound a little bit. Whoops, sorry about that. Okay. And you're going to invert the open end of the tube. So there's one end that's open and one end that's closed. You're going to tap the open end into the material. And if you look now, I have gotten a small amount of material into it. And then I'll turn it upright, and you can simply tap, although that hasn't very efficiently brought the sample down. So we can use a long, thin tube. In this case, I have just a burette whose cap I've taken off. Okay? And we simply drop this burette. I'm out of the frame right now, but what I'm doing is going to drop the tube from the top down into the bottom, and you'll see it tapping at the bottom. Okay? And that's going to give us a nice gentle tap. You might have to do it a couple of times. Now our sample is nice and tightly packed. I would say that this sample, you can compare it to my finger, okay, is a little bit too long actually in this case. You can see I've got almost the width of my pinky fingernail there, and that is probably too much of a sample for a melting point analysis. You more likely want a sample that's about half of that in size. And so in this case, I'm going to use a much smaller sample now. Zoom back in if I could. Okay. Once again, I'll pack it, dropping it down. Okay. Usually, if you have little crystals, you get a nice, quick, easy pack. And then you can see I've got a much smaller sample. A larger sample would naturally lead to a larger melting point range because it'll take more energy and time to melt that in the melting point analyzer. So I would take my packed tube, as I showed you earlier, insert it into one of the slots. I would turn on the instrument, and then I want to begin to gently heat. Now, if you have no idea what your material is, the first time you conduct the melting point, you might heat a little more rapidly at a setting of maybe 6 or 7, or that would be 60 or 70% of your power. This will increase the temperature more quickly, and you won't get a very accurate reading of the melting point of your material. But you can prepare a second sample, cool down your melting point analyzer briefly, and then after it's cooled to well below your rough temperature for melting point, say you got 100 as the melting point, I would recommend you let it cool down to at least 80 before you try your second sample. Okay? Then you could heat that second time at a lower setting, maybe a 50%, all right? So that the temperature isn't changing quite as rapidly, and you get a much better, much more accurate value for the melting point of your sample. Okay? Then you would also prepare the a pure sample of your known, of your what you guess to be your unknown. Okay? And you would prepare a mixed sample of your unknown and the pure. And you would measure those two in a subsequent experiment as well, side by side. If you cannot identify your sample immediately, like if there's more than one possibility, you would want to make mixed samples with each individually, each of the potential identities of your unknown, so that you could see which one maintains the narrow range when you mix them together. Right? So melting points are a pretty vital part of work in organic chemistry. Anytime you make a new compound, it's one of the classic things that you do would be to first conduct a melting point analysis and compare it to a known sample to hopefully confirm a successful synthesis. So I hope you'll enjoy today's experiment, and there is a lab report sheet that you'll complete and answer a variety of questions, which are all addressed in the introductory materials of the laboratory description in your manual, as well as things I've commented on throughout the video today. Take care and enjoy the experiment.